I have a simple example in the Abaqus Learning Edition. It is a simple bolt problem. You can see it here in the left window. The model consists of two flanges, and then there's a bolt going down the middle. And I have all internal loads. I have the bolt load, and then I have a thermal expansion step. So I should have no net load on this structure. So you might think that you could get away with no boundary conditions. I do have static procedures here. But what would happen if I tried to do that? So I ran this model twice, once without boundary conditions at all, except the one that's involved with the bolt loading. And then I ran it again with statically determinate boundary conditions. So step 1 is to apply the bolt force. Step 2 is to fix the bolt force. And then step 3 is to thermally expand the structure. The two flanges have a different thermal expansion, a higher thermal expansion than the bolt. So what happened when I ran this without the boundary conditions? Let me open that result here, and I'll do it in this window. So I got through the bolting step, and I have the same model in both windows here, but I guess that's okay. Let me change this one to the case that did have the boundary conditions. And you can see that this model without the boundary conditions didn't make it past step 1. If I go to the monitor here, I can see that the job failed at the beginning of step 2, so I didn't get very far. And here's the case with the boundary conditions, and I'll show the boundary conditions here in a minute. And this model ran all 3 steps, and you can see the result here. So there's the result. And so I have some stress there at the end of step 3, which is the thermal expansion step. But, what about these boundary conditions? What do those boundary conditions look like? Well, let me go to the load module and turn those on, or activate them. So here I have them turned off for the case without the boundary conditions. So I'll turn them back on. And then you can see what they are. So this first boundary condition is the constraint on this node at this corner. I'll show you what it looks like. It's all 3 degrees of freedom at that node, so it's a solid mesh, of course. And then boundary condition 2 is at this other node here in the 2 and 3 directions. And so that would be in this direction and this direction. And then I have another boundary condition at this node in the back here. And this is in the 3 direction. So these are 6 boundary conditions, and I should be able to figure out what those are based on the applied load. But the applied load is 0. It's all internal. So what happened to the reaction forces at those nodes? So if I go into my result here with the boundary conditions and plot the reaction force, let's do that. Let's change the result to the reaction force. And the reaction force here is extremely large, but this is the reaction force at the bolt pretension node. So it's at 7,143. At the beginning of the step, it's at 5,000. That's the applied bolt force, and then the thermal expansion makes it bigger because the flanges are expanding more. But what about the boundary conditions that are the statically determinate boundary conditions? What is the reaction force there? So let me remove from the display the bolt pretension node. So there it is, and I'll remove that. So now you can see that the reaction force, the magnitude of any reaction force other than that bolt pretension reaction force is very small. So I need these very small forces to counteract the vagaries of the contact. I believe that's what's causing that. And we do have discretized contact. So I do have a little bit of leftover force from the contact. And you can see that most clearly if I plot the magnitudes of the, or if I plot the components. So let me plot RF1. RF1 is extremely small. RF2 is extremely small. RF3 is very small, but much bigger than the other two. And you notice that the contact would be in the 3 direction. The normals of the contacting surfaces are in the 3 direction. So this is just a little demonstration on the reaction forces in a model that has internal loads. So this comes up fairly often when you're doing static analysis and you have something like bolt loads or whatever, and the structure is more or less free, but you need these boundary conditions to get the Abaqus standard solution method to complete, because you can never have truly completely balanced loads internally. It's very difficult.